Today's lesson is called Simplicial Complexes, and this is a day where we start doing mathematics on computer. We won't be able to do topological data analysis yet, because as you may have understood, I want you to really understand the theory, the mathematical background of it before going further. And the theory of topology on a computer starts with the following question: how can I do topology on a computer, right? So this is called combinatorial topology. And we will learn today how to represent topological spaces on a computer. So I will start by defining simplicial complexes. We will see how they are linked to topology. In the way we will be able to define a new invariant that is called Euler Characteristic. So this will last 30 minutes, something like that. And then we will do a tutorial. So I will show you how we can do it in practice in Python. So in order to describe a topological space on a computer, we will decompose our topological spaces in simple pieces, in small pieces. And the pieces we will use are called standard simplices. So here is the definition of the topological standard simplex. Take an integer, n, and define this subset of R to the n plus 1. It's written here. So this is the set of all convex combination of coordinates. The sets of points of Rn plus 1 with all coordinates positive and such that their sum is equal to 1. 3 examples. The first standard simplex, delta 0, is a subset of R 0 plus 1, R1, and it consists simply in one point, the point of coordinate 1. Delta 1 is a subset of R2, and it is, as you can see, this straight line between the points 1, 0 and 0, 1. Delta 2 also is a subset of R3. And there is an interesting way of seeing that. Let me introduce the notion of Covex Hull. Take any collection of points in Rn, A1, AK. I define their convex hull as this set. So this is a set of linear combinations of the points A1, AK, such that the coefficients are all positive, non-negative, and such that their sum is 1. All right? And thanks to this notion, we can say that the standard simplex simply is the convex hull of the standard, the canonical basis of Rn plus 1. The canonical basis being the vectors E1, E2, etc., En plus 1, where Ei is a vector with 0 coordinates everywhere, but at the ith coordinate, where you have a 1. All right. So when we have a standard simplex like that, we can endow it with the subspace topology of Rn plus 1. And keep that in mind for the moment. Have this mental picture that a standard simplex delta 1, delta 2, delta n is defined by n plus 1 vertices. Okay. So this is topology. Now let's do combinatorics. I will start by defining a simplicial complex as a combinatorial object as follows. I take V any set that I call the set of vertices, and I define a simplicial complex over V as a collection of subsets of V, this collection being called K. The elements of K are called simplices, and I have one axiom. For every simplex in K, that is for every subset of V that I chose, I ask that all the subsets of sigma are also in K. So let me give you an example. I take V as a set of vertices to be the set with 3 elements, 0, 1, 2. And I consider K, this simplicial complex, which consists in 3 subsets with 1 element and 3 subsets with 2 elements. This is a simplicial complex because if I take any element of K, for instance, this one, 0, 1, each of its subsets, for instance, the subset 0 or the subset 1, is already in K. For instance, this subset here, 0, is in K. So the elements of K are called simplices, a simplex, mainly simplices, and the subsets of a simplex are called faces of the simplex. Lucas asks, is there a reason to avoid the empty set? The empty set is not in the definition. It will not matter to have the empty set or not. This is not important. Yeah, remark that these elements are subsets of V, but I do not write them with curly brackets as we do usually for sets, but with square brackets. This is just a convention. Okay. And you can draw a simplicial complex by simply drawing the vertices, the elements of the set of vertices on the plane. And then for every simplex, you draw the simplex. So for instance, 0, 1, this will be an edge. I draw the edge 0, 1. 1, 2, this will be this edge, and 2, 0, this one. So this drawing represents my simplicial complex. Another example, I consider this larger simplicial complex. I added the simplex 0, 1, 2. This is still a simplicial complex because all the faces of this simplex are already elements of my simplicial complex, right? And now if I want to draw it, I have to make clear the fact that 0, 1, 2 is an element of the simplicial complex. So I fill the triangle 0, 1, 2. Another example, which is a counterexample, this set K is not a simplicial complex, right? Because we have a simplex 0, 1, 2 that admits a face which is not in the simplicial complex. As you can see, 2, 0, this is a subset of 0, 1, 2, but 2, 0 is not in this simplicial complex K. not in this set. So K is not a simplicial complex here. And I draw that by drawing a dashed edge. Another notations, I can define the dimension of a simplicial complex. First, I define the dimension of a simplex. If I have sigma a simplex, that is an element of the simplicial complex, its dimension is defined as its cardinality, its number of elements, -1. Okay? For instance, the edge 1, 2 has dimension 1, equal to 2 minus 1. This makes sense because an edge, topologically, is something, a topological space of dimension 1. A triangle has dimension 3 minus 1, 2. So this is the dimension of the simplices. And now the dimension of the simplicial complex is the maximal dimension of its simplices. So this simplicial complex has dimension 2, because the maximal dimension you can find in its simplices is 2. All right. So this is a combinatorial definition of a simplicial complex, meaning that there is no topology here. It's only finite sets. And of course, we'd like to put a topology on it. So we'll start with abstract definition of the topology we can put on a simplicial complex. And then I will explain a simpler way to understand this topology. To give a simplicial complex a topology, we will use the subspace topology of the Euclidean space. To do so, take a simplicial complex, K, with vertex sets that I denote 1, 2, until n. And for every I in this vertex set, consider the ith canonical basis vector of Rn. There is a mistake here. Okay. Then I will consider a subset of Rn that I call K with 2 bars. And this subset is defined as the union of Covex hulls of the simplices of K. I take every simplex of K, the abstract combinatorial simplex. For every simplex, I look at its vertices. Then I look at the corresponding canonical vectors of Rn. And then I consider the convex hull. This is exactly this drawing here. But we are in large dimension. And this set, K between 2 bars, is a subset of Rn, not Rn plus 1. And I will call this subset the topological realization of my simplicial complex, K, where I endow this subset of Rn with the subspace topology. Okay, so thanks to this definition, I am allowed to go from an abstract simplicial complex to a topological space. So this is a bit abstract. We can do simpler. If you are able to draw your simplicial complex in the plane, drawing meaning without self-intersection. You have to make sure that the edges, the simplices, do not cross each other. If you are able to draw your simplicial complex in the plane, then this topological realization simply is this subset endowed with the subspace topology of R2, the plane. Example, this simplicial complex, K here, it has dimension 2. We have one simplex of dimension 2, 5 simplices of dimension 1, and 4 simplices of dimension 0, 4 vertices. I can draw it without auto intersection like that. So I can say that the corresponding topological realization is simply this subset of the plane endowed with the subspace topology.
When we consider this simplex, are we actually, and we do it with a topology?
Yeah.
Are we dealing with the inside of the purple area, for example? Is it part of our set, or just the edges and the vertices?
The most convenient way to do that is by considering only the interior, not the boundary of the simplices. You can define, these are really two objects of different nature. This one really is a combinatorial object, and this one really is a topological object. But the most convenient way to see it is to say that 0, 1, 2 will denote the interior of the triangle. There is also another way of defining the topological realization of a simplicial complex, and it consists in gluing the simplices. I do not write the definition here, but it's nice for the intuition. Each of these simplices are in correspondence with a standard simplex, as we've seen in the beginning. What you could do is say, okay, for each of these simplices, I take the corresponding standard simplex. It is a topological space, and then I glue all of this standard simplex to obtain my whole simplicial complex. This is called a quotient in topology. Okay. And now we can talk about triangulations. So the aim of simplicial complexes is to represent topological spaces that we are studying. And this representation is called a triangulation. So the definition is as follows. Take a topological space, xt. X is a set, T is a topology on X. A triangulation of my topological space X is a simplicial complex K such that the corresponding topological realization is homomorphic to X. Example, if I take K equal to this simplicial complex, I can draw it like that on the plane. So this is a circle, a triangle, and we've seen 2 days ago that a triangle is homomorphic to a circle. So I can say that this topological realization is homomorphic to a circle. So according to the definition, this simplicial complex is a triangulation of the circle. And now you are able to manipulate the circle on your computer simply by using this structure. An example of dimension 2, I want to triangulate the sphere of dimension 2, the sphere in R to the 3. It is simply this simplicial complex. I have 4 points that I represent in the space, and I consider all the subsets with 0 elements, 1 element, 2 elements, and 3 elements of the 4 points. And as you can see, I obtain a tetrahedron, an empty tetrahedron. I only have the faces, and this is homomorphic to a sphere. So this simplicial complex, K, is a triangulation of the sphere. There is a facultative exercise in the notes where I ask you to find a triangulation of all the spheres of dimension n. It is really the same idea that these two examples. A remark: all topological spaces are not triangulable. It is not possible for every topological space to find a simplicial complex that is a triangulation of it. Fortunately, most of the topological spaces we like and we study in math in low dimension are triangulable. However, when a topological space is triangulable, when you can find a triangulation of it, there exists an infinite number of triangulations. For instance, these 3 simplicial complexes are polygons, and as any polygon, they are homomorphic to the circle. So here we have 3 different triangulations of the circle. I have a question of Claudio. In this example, if you had also 0, 1, 2, 3, it will be homomorphic to the dot. It will be homotopy equivalent to the dot. Recall that the equivalence relation that allows to retract something onto a point is the homotopy equivalence relation. The homomorphism equivalence relation does not allow to retract objects. So if you were to add the simplex 0, 1, 2, 3, you will obtain a closed ball of dimension 3. Okay. Last section before we go into coding. Simplicial complexes allow to define a very famous and a very important invariant of topological spaces that is called the Euler Characteristic. And this is really simple to define. Take a simplicial complex of dimension n and define this quantity, P of k. So this is the alternate sum of the number of simplices of dimension I, where I goes from 0 to the dimension of your simplicial complex. This quantity is called the Euler characteristic of your simplicial complex. For instance, if I take my triangulation of the circle, K, I have 3 simplices of dimension 0 and 3 simplices of dimension 1. So its Euler characteristic is -1 to 0 times 3 and -1 to 1 times 3. This is 3 minus 3. This is 0. The Euler characteristic of the circle of this simplicial complex is 0. Let us consider the sphere. The sphere has 4 simplices of dimension 0, 6 simplices of dimension 1, and 4 simplices of dimension 2. So its Euler characteristic is 4 minus 6 plus 4, and this is 2. The Euler characteristic of this triangulation of the sphere is 2. Okay. Is it an invariant? And what does that even mean to be an invariant of topological spaces? Because as you can see, the Euler characteristic is defined at the level of simplicial complexes. And I would like to define the Euler characteristic for topological spaces. So there is this natural definition. What is the Euler characteristic of a topological space? It is the Euler characteristic of any triangulation of my topological space. In other words, if I want to find the Euler characteristic of a given topological space, first I find a triangulation, and then I compute the Euler characteristic of the triangulation. So there is 2 issues here. First, my topological space must admit a triangulation, because if he has no triangulation, I cannot compute the Euler characteristic. And the answer to this issue is that all topological spaces does not admit. So I was saying that in order to define the Euler characteristic of a topological space, we start by triangulating it, and then we compute the Euler characteristic of our triangulation, our simplicial complex. I have a question of Lucas. In order to fix my ideas, could you draw the topological realization for n equals to 2? The topological realization of what? Of the simplicial complex? Oh, of the standard simplex? Yeah. It is here. If you take n equals to 2, the standard simplex of dimension 2 is a triangle. You take 3 points and you fill in the triangle. Is it your question? Okay. You're welcome. And I was saying that there is 2 issues with this definition. The first issue is that all topological spaces does not admit a triangulation. So this is not possible to define the Euler characteristic of all topological spaces. This is how it is. And Lucas asks, Is the Euler characteristic always non-negative for simplicial complexes? Not always. Can be pretty much anything. For instance, if you take 4 vertices and 6 edges, you will obtain 4 minus 6, which is minus 2. If you take only the skeleton of the sphere. Second issue, when I say that the Euler characteristic of a topological space is defined as the Euler characteristic of any triangulation, I have to make sure that all the triangulations that X admit have the same Euler characteristic. Otherwise, I wouldn't have a unique Euler characteristic. And this is not a mathematical definition. In other words, I have to make sure that if I have two triangulations K and K prime of a topological space X, then the characteristics of K and K prime are equal. Fortunately for us, this is true. Any two triangulations of the same topological space have the same Euler characteristic. Though we will need to develop some theory to prove that, and we won't have the time in this summer course. So please accept this statement. Okay, now we can talk about Euler characteristics of topological spaces. For instance, the Euler characteristic of the circle is 0 because this simplicial complex is a triangulation of the circle. The Euler characteristic of the sphere is 2. As we've seen before, this simplicial complex is a triangulation of the sphere and it has Euler characteristic 2. Mental exercise. These 3 simplicial complexes are triangulation of the circle, and you can verify that they all have the same Euler characteristic. Can I? Yeah. For instance, this one, its Euler characteristic is 3 minus 3 equal to 0. This one is 4 minus 4. And this one, 1, 2, 3, 4, 5, 6. 6 minus 6. Okay? I have a last thing to say. Also something that we won't be able to prove. If I have two topological spaces X and Y that are homotopy equivalent, then they admit the same Euler characteristic. Okay? So, as we've seen the other days, this means that the Euler characteristic is an invariant of homotopy equivalence classes of topological spaces. And the main use of this information is that we can use the Euler characteristic to prove that two topological spaces are not homotopy equivalent. We just compute their Euler characteristic and check whether they agree or not. For instance, we computed the Euler characteristic of the circle and the sphere. The circle is 0, the sphere is 2. so they are not homotopy equivalent. And I also propose an exercise in the notes. Thanks to this notion of Euler characteristic, you can show that the topological spaces R3 and R4 are not homotopy equivalent. This is something that we haven't been able to prove with the number of connected components, the other invariant we had in the homotopy equivalence classes. All right. This is the end of the theoretical part. Please, everyone, follow this link, and we will do the tutorial together. And if you have any question, please ask. Oh yeah, thank you, Lucas. This is a mistake that I wrote here. R3 and R4 are homotopy equivalent. Thank you for your correction. The statement is are not homeomorphic. Thank you. And another Lucas asks, in definition of topology, you corrected Rn+1 to Rn. Yeah. When you define the topology of the topological realization of a simplicial complex. Where is it? This n+1 should be n. Yeah. Is that your question? Thank you. Yeah, also, we will go slow today in the tutorial for everyone to be able to follow what we do. For those who want to go faster, you can have a look at this tutorial of the Goody library, which introduces the Simplex Trees. When we will do topological data analysis, we will use a more rich structure than simplicial complexes. And this other structure is called Simplex Trees. So if you want, you can have a look.
Rafael, excuse me.
Yeah.
The link you just sent, the second one, says that it's not available.
The first one or the second one?
Second one.
Oh. Or maybe because I have a special access. Let me
it
check.
says that page not found.
All right, let me. Are you able to? No, this is the same link. Are you able to follow the link I sent in the chat?
Yes, it works now.
Okay. All right. And I also send the actual tutorial. Okay, you should be able to see my notebook on my screen. So I will start by introducing the very basics of this notebook. And then I will let you some time to code on your own, and we will correct together. So first, let me explain what we have. All the TDA we will do will use the Goody library. You have a lot of different libraries to compute persistent homology and to do topological data analysis. Goody first is the one I know best because it has been developed by my team in Paris at INRIA. This is not the fastest library, but it does a lot of things, not only the usual notions of topological data analysis.
It is not the fastest in Python.
No.
What is the fastest? Giotto? What's the fastest one?
What is
What's the one that's faster than Goody?
Do you know Ripster? Ripster?
No.
Yeah, this one. It is known as the fastest library to compute persistent homology. But it is very restricted to the persistent homology of the RIPS complex of point clouds.
Okay, thank you.
So this is Goody. I use also NumPy, of course, because we will compute numeric values like distances between points and stuff. So we have NumPy. And network X is not really mandatory. I simply use it to draw simplicial complexes, because in network X, you can define graphs, and you have some very cool tools to plot graphs. So this is why I use this library. And in the second box, you can see 4 functions I define. So as this is the first tutorial, I already coded some functions to simplify your computations, but you will be able next week to understand all of that. Okay. So let me restart my kernel. I will first show you how to implement a triangulation of the circle in Goody. The structure of a simplicial complex in Goody is called a simplex tree. Okay, so if I want to create a simplicial complex, I call Goody.simplex tree up, and this creates a structure. The simplex tree in Goody. Okay. Then I will add one by one all the simplices of my triangulation of the circle. So I have 3 vertices, 0, 1, 2, and 3 edges, 0, 1, 1, 2, 2, 0. I start by adding the vertices. And I wrote for you a function that prints the list of the simplices of the simplicial complex. So if you do that, you will see that at the moment, our simplicial complex contains only 3 simplices of dimension 0, the 3 vertices. Okay. Now I will add the edges. I have 3 of them. Same line, simplicial complex, dot insert. And I put my simplex in square brackets. Up. Goody says true. That means that it has been able to add the simplices to the simplicial complex, and that the simplices were not already present. If they were already here, Goody would have said false. Okay. No, I verified that the edges are correctly added, and I see that my simplicial complex has all the simplices I wanted. Okay. I also give you this function, draw simplicial complex. You simply put your simplex tree in parentheses, and network X take care of representing, of plotting, of drawing your simplicial complex in the plane. And so we are happy because this is effectively what we wanted, a triangle. Okay. So this is a bit boring to add vertices and then to add edges. There is a way to do it faster in the Goody library. If you add a simplex, all the faces of the simplex are added at the same time. For instance, if I still want to define this simplicial complex, but faster, I will say, okay, I call it simplicial complex 2, Goody.simplex tree, and then I add directly the edges without adding the vertices. And as you can see, vertices are already there, because when I added the edge 0, 1, Goody also added the vertices 0, 1. And an even faster way to do that, sim complex 3, I add the whole simplex 0, 1, 2. So I add also all of its subsets. And then I remove it. I remove 0, 1, 2. So what I get at the end is the same thing. Okay. Be careful with this function, remove maximal simplex. A maximal simplex is a simplex that is not a face of a larger simplex. If you try to remove a simplex that is not a maximal simplex, this would crash. For instance, here, if I want to remove the edge, the vertex 0 of my simplicial complex, this is not a maximal simplex because you have this edge 0, 1 that contains 0. And so I think that Goody will not be very happy. Maximal simplex 0. Yeah, my kernel is dead. So be careful. Up. And last thing I want to show you. I wrote also for you two functions that allows to compute invariance that we've defined before. The first one is number of connected components. You simply put your simplicial complex inside. This argument is not important. Verbose simply means that do you want that sentence is written? Let me show you. When I use this function, I can read the simplicial complex admits one connected component. If I write false here, oh, it's still right. All right, there is an error in the function.
Professor?
Yeah.
Is it this connected component relative to the topological space?
Yeah,
it's that connected component we study later, right?
Yeah. When I say the number of connected components, this is the number of connected components of the topological realization of your simplicial complex.
Okay. Is there a way to draw the topological realization? I think it's the thing I'm most interested in.
Yeah, you can use this function, draw simplicial complex.
But the topological realization, is it possible to draw the R3 and the triangle in the R3?
So this simplicial complex here only has dimension 1, so there is no triangle. If you had the simplicial complex of larger dimension, for instance, I could consider this one, simplicial complex of dimension 2. This is a simplicial complex that contains the simplex 0, 1, 2. And I want to draw it. As you can see, the triangle is not drawn. This is because network X, the library, only plots edges and not triangles. So unfortunately, this function here does not represent the real simplicial complex, but only the underlying graph. If you want to use, if you want to draw the triangles, you will have to use another library like matplotlib or something like that. Is it your question?
Okay. Yes, thank you.
All right, so number of connected components, and finally, Euler characteristic. Same thing. You put your simplicial complex, and this is not important. I can read the simplicial complex has Euler characteristic equal to 0, and this is what we computed in the lesson. Okay, this is it. I will give you 5 to 10 minutes to do the first exercise, exercise 22. Please build triangulations of the letters of the alphabet, at least from A to H. A, B, C, D, E, F, G, H. I give you an example here. And then I want you to compute their Euler characteristics. Okay. So I will stay here to help people that need help. You can mute your computer so that you won't be disturbed by me. Oh, yeah. Thank you. This is not. Oh, yeah. Thank you. Does anybody need help to install Goody or to run the code? Yeah, Lucas, the number of connected components of a simplicial complex only depends on its graph. So the graph generated by the simplices of dimension 0 and 1 is called the one skeleton.
Sorry, what's the exercise that we're supposed to do?
Exercise
All of
22.
these?
22, please do the letters, triangulate the letters from A to H.
Okay.
Tiago asks, can you give an idea on how Goody calculates the number of connected components? The way Goody calculates the number of connected components is actually the way it computes the homology. The homology being an invariant, the best invariant that I know, that we will define next week. But basically, you start by adding the vertices in the plane. So if you have, for instance, 3 vertices, you have 3 connected components, and then you add the edges. And for each edge you add, you see whether it connects 2 connected components. For instance, if you have 3 points, first you have 3 connected components, add the first edge, you have now only 2 connected components, add the second edge, you have only 1 connected component, and then you add the last edge, you still have 1 connected component because these 2 points were in the same connected component at the beginning, just before. So basically you add edges and you see if you connect connected components that were not connected. So Hannibal, see if I am correct. The topological relation is comprised of all simplices except for the boundary. In case of a triangle with node A, B, and C, we don't consider the simplex ABC. I'm not sure to understand what you mean. I will write a simplicial complex in the chat. Yeah, this simplicial complex you wrote does not have the field triangle.
Should we move to exercise 23 and 24 and the rest, or
Yeah,
we stop at 22?
they are in order of, yeah. Yeah,
Sorry,
Guillaume.
one more question, Rafael. What's the bouquet of n circles?
Oh, the bouquet of n circles is n circles that are connected by one point. You glue n circles.
Okay.
Yeah. I make a drawing. Wait. Bouquet of n circles. This is, for instance, a bouquet of 3 circles. So Guilherme, yes, this thing is a P. You can see that this is something which is homomorphic to P.
So P and A, they do not have the same Euler characteristic, but they are homotopy equivalent, right?
No, they must have the same Euler characteristic.
If one of them is 0 and the other one is 1. See?
1, 3, 2, 4.
It shouldn't make a difference, right?
Oh, but this is not a P. Sorry, this is not a P because you have the inner triangle here.
Mm.
But this is not drawn. My function draw simplicial complex does not draw triangles, unfortunately. It should be 1, 2, 2, 3, 3, 4, and 1, 3. This is a P.
So the orientation matters.
No, no, no. The difference between what I wrote here and what you wrote in the chat is that the simplex 1, 2, 3, the whole triangle is not present in my simplicial complex.
Oh, I see. I see. I understand. Okay,
So
thank you.
this is different. This will be a field P that you defined.
Yes, but do you see my dilemma, right?
Yeah.
I didn't understand that they were not the same.
Yeah, this will be absurd, of course, if they are homotopic. If they are homotopic, they have the same Euler characteristic.
Rafael, for the I cannot draw an E. Can you help me with that?
Yeah, of course. So drawing and E. I will say simplicial complex equal Goodip simplex tree. I would like to write this. Up. So
Work.
the first one is 0. 0, 1, 1, 2, 3, 4, 4, 5. Oh yeah, that's all.
Professor,
Yeah.
the topological realization is a topological realization of the letter E in R6?
Yeah. So the topological realization of the letter E, as I defined it, is a subset of R6 endowed with a subspace topology.
Okay.
But this topological space also is homomorphic to this thing in R2.
I understand.
And when you talk about topological spaces, it does not really matter which exact topological space it is. You only are interested in the homeomorphism class of this topological space.
Okay.
And
Makes sense to me.
okay,
Okay. Thank you.
please.
1, 2, 2, 3.
And then, Luisa, what is your trouble with the letter G? Oh, you can. Yeah, it is curved. So you have to triangulate it. There is not a unique way of triangulating it. So you could say simply, okay, I have a triangulation with only 2 points. So this will be simply this.
I don't know, Raphael, the triangulation is not unique, right? Because you could do a C like that, right?
Yeah. It is never unique. And so we do topology, Doc. So we are only interested in the homeomorphism type of our topological spaces. But in some areas, for people who do meshes, for example, in math, they have to have a huge number of points.
Rafael, let me get this straight. So Y and E, they have the same simplicial complex drawing, right?
Why?
So the
You
E and Y.
You cannot say that they have the same. You can say that they admit both the same triangulation.
Okay, triangulation. Okay, okay, but what I said is true.
Yeah, exactly.
So is there a way to uniform to make it a standard so you don't have this unidentifiability of how to triangulate?
No, this is not an identifiability for us, because for us an I is a G. We do not make difference between I and G topologically, because they are homomorphic.
Okay, so it's a little bit a higher level than just the points and the curvatures and etc. It's just we need to understand that they are the same topological object, right?
Exactly. That's it.
Thank you.
When we will do topological data analysis in 2 weeks, we will put a little bit of geometry. So we will be able to tell that an I is different from a G. But at the moment, this is the same thing for us.
Rafael, sorry, I kind of missed the discussion. Were you guys saying the letter E is homeomorphic to the R6? Or did I understand things
No,
incorrectly?
the letter E, I is, I is, this one is homomorphic to
I
G.
or
I.
no, okay, this one I got it. But I think it was Lucas who asked the question before about the letter E
Yeah.
being homeomorphic to the R6 or something like that.
No, yeah, because I define in the lesson the topologicalization of a simplicial complex. And in order to define the topologicalization, I embedded the simplicial complex in Rn, where n is the number of vertices of my simplicial complex. So the topologicalization of E lives in R6.
Okay.
But what I said is that you can also see it in R2, because I am able to draw E in the plane without crossings. So you can also see the topologicalization in the plane. You do not have to go into R6.
Cool. Thank you.
All right. Do you have any question about exercise 22? If this is okay, I will go to the next one. Okay. So I want to triangulate the bouquet of n circles. I will propose a solution. Something like that.
We're not changing the value of the vertices. They're always the same.
Oh yeah, right. Thank you. Cool. So this is a way of triangulating the bouquet of n circles. I took the most simple triangulation of the circle with 3 vertices. And I say that one of the vertices is always the same, 0. And let's see its Euler characteristic. So as you can see, for any value of n, the bouquet of n circle has Euler characteristic 0. Also, something interesting that may happen if I take a n too large, for instance, let's take 10. Now this is okay. Yeah, here you can see that.
Sir,
Yeah.
sorry, you are computing the Euler characteristic of the other subcomplex.
Oh, right. Thank you. Oh yeah. So I was absolutely wrong. What is the Euler characteristic of n circle? I don't even know. For 0, it's 1. For 1, it's 0.
It's n minus 1.
Yeah. Seems like the Euler characteristic of the bouquet of any circles is 1 minus m. All right. You can begin to see that the Euler characteristic is something that catch the number of holes in your simplicial complex. If I were to add the triangles, the Euler characteristic would not depend on n. Okay.
Rafael, can you explain me again what is the difference?
All right. So what I should have done before this lesson is to write a function draw simplicial complex that draws the triangles, but it does not. So take care when you look at a representation of a simplicial complex. Take care if the triangles are in the simplicial complex or not. For instance, here, the simplicial complexes, the triangles are not in the simplicial complex. You can see it. What is print simplices?
The same problem we faced with the letter E, right?
The exact
The letter P.
Yeah, the exact same, exactly. You can see
Got
that.
it. Mm-hmm.
Yeah, okay. I have no triangles here, but when I do that, yeah, I can see them. So the Euler characteristic is different. All right. Yeah, let me do a comment. Sometimes the library network X does not plot the graphs very well. As you can see here, the triangle 0, 5, 6, its edges cut the edge 5, 6, cut the edge 0, 4. Okay, because the points are chosen basically at random. So take care that if edges cross, the drawing we have is not a faithful representation of our simplicial complex. In other words, this subset of the plane does not have the same topology than the actual topological realization of my simplicial complex.
But that's just a matter of representation, a graphical representation, because internally the program knows that they are not intersecting, right?
Exactly. Yeah. Just a matter of understanding the drawing. Okay. I would like to do this last exercise with you. And then I will let you with the two last, which are a bit more complicated than the others. The first exercise for you, 25. I don't know how you call that, but I think it's usual in data analysis. You compute the graph, you take a parameter, you have points in the Euclidean space, and you put an edge between 2 points if they are close to each other. You select a parameter R, and you compute the graph where an edge is present if the points have a distance lower than R. So what I want you in this exercise is to compute this graph for several values of R and see how the invariants behave. And exercise 26, this is an exercise where you have to build a random simplicial complex, a random graph, and then to see how what is the behavior of the invariance of this random graph. So don't hesitate to get in touch with me this weekend if you have any question about that. Exercise 24, implement the triangulation of the torus given in the notes. So where is it? Yeah, this one. So the torus, this is a very interesting surface, a two-dimensional object. And the torus, as you may know, you can obtain it from a square. If you take a square, you identify the opposite edges of the square, like that. You obtain a cylinder. I don't know if you can see this, but this is a sheet of paper, which is a square. I can identify opposite edges to obtain a cylinder. And then if I identify the circles at the boundary, hop, I obtain a torus. And this is what we do in this example. We have a triangulation of the square, but we say that these vertices are the same. So we'll just do that. Oh. So what I get is a simplicial complex that has a Euler characteristic -1. Do you obtain the same?
Does it mean the torus has one hole? Or there's nothing to do with it?
It's a bit more complicated than that, because you can understand the Euler characteristic as the number of holes for graphs in the plane. If you have a graph in the plane, for instance, the simple letters we have, or the bouquet of circles, the Euler characteristic is related to the number of holes. But for higher dimensional spaces, this is not so easy to understand.
Raphael, could you please paste the Taurus in the chat?
Can I what? Oh, put the code?
Yeah.
Yeah, of course. And if I plot the simplicial complex that I have, this is very disappointing, because the function does not know how to plot two-dimensional simplicial complexes.
To be honest, it's hard to just by looking at the figure, it's hard to say that it's a torus. It's actually impossible. I would never
Yeah.
imagine.
Yeah, right. You could try to specify the position of the points in the space. You can do that. You can design a function that will place correctly the points and put the triangles. But the question of representing a simplicial complex in the space nicely is a complicated question mathematically. Lucas says each circle section becomes a triangle. I don't understand what you mean.
It's because when I imagine a way to do the torus using the points, I would imagine first starting with a circle, with a triangle, and out of this triangle, draw another triangle. It will be like an annulus, and I will draw the 3D part, the depth part of the torus as a triangle when you rotate this what you already have. So you would end with 9 points. That's what I think it is there.
Yeah, right. And I think this is exactly the triangulation you have here, because the torus is the product of two circles, and you say that the first circle can be triangulated with a triangle, and the second one also. So you have the two triangles. Yeah, exactly. This is a nice description. Oh, there is a mistake here. 7, 8, 5. 7, 8, 6. There was a mistake. I have a Euler characteristic 0 now. Ah, Jesus. So Guilherme, what is the simplicial complex you sent?
I imagine as a torus embedded in a bouquet of circles.
This is a bouquet of Taurus.
Or something like that. I'm not sure, because in the 1, 2, 3, 4, 5, and 6, yeah, correct. I use n equals 3. You draw a bouquet of circles, right? So you have something very exquisite.
Thank you for your nice simplicial complex. All right, I think we'll stop here. Is there any question? Okay. Nice. I think I have a conclusion slide. Yeah. To conclude, I'd like to say that I show you today how to represent a topological space on a computer. So simplicial complexes are the very basics of combinatorial topology. And on the way, we have been able to define a new topological invariant. So for the next week, I'd like you to do exercises 20, 23, and 24. Oh, we already have corrected 23 and 24. So have a look at 25 and 26. And we correct that. 25. 26 being a way harder exercise than the other. And that's it. Thank you very much, everyone.